His name was Heinrich Bauer. He was 31 years old, broad across the shoulders from 11 years feeding hot billets into the throat of the Schmiede press at Krupp's Essen Works. And on the morning of March 4th, 1897, he arrived 7 minutes early for his shift. His foreman noted it. Other men noted it too. Not because it was unusual for Bauer to be early, but because of what he said when he crossed the forge floor and looked up at the machine that had defined every waking hour of his adult life. He said, "She's quiet today." She was. The 900-ton hydraulic steel press stood in its iron pit like a cathedral organ built for a god with no interest in music. 60 feet of forged column, reinforced frame, and descending ram, capable of applying force sufficient to flatten a standard rail blank in 4.3 seconds. The floor shook when it moved. Men who worked near it for more than 3 years developed a permanent tremor in their left hand. The noise it produced at full compression was compared, by plant engineers in their internal reports, to artillery detonating underground. That morning, it was silent. Heinrich Bauer pulled on his leather apron, checked the water pressure gauge on the south column, a habit so ingrained it required no conscious thought, and took his position at the billet feed station, 3 feet from the descending ram's operational arc. By 10:40 a.m., he was dead. The press had not malfunctioned. The hydraulic seals had not failed. The pressure gauge he had checked that morning was functioning within acceptable tolerances. Every system that the Krupp Engineering Directorate had certified as safe was, by every available measurement, operating exactly as designed. And that is the question that has never been fully answered. Not in 1897, not in the decades of industrial expansion that followed, when Germany's steel output tripled and the great presses multiplied across the Ruhr Valley like iron gods demanding tribute. Not even now, when the records have been partially declassified and the weight of what those machines produced and consumed can finally be measured in full. The 900-ton press built a nation. It forged the rails that stitched an empire together. It compressed steel into forms that no previous century had imagined possible. It also had a relationship with the men who served it that no corporate report ever described accurately. What happened inside those forge halls, to the metal and to the men, is a story Germany told itself one way for 100 years. The truth is considerably heavier. There is a particular kind of institutional pride that functions like a closed valve. It allows pressure to build. It permits no release. And in the industrial culture of late 19th century Germany, specifically within the Iron Kingdom that Friedrich Alfred Krupp had inherited from his father and was in the process of transforming into the most formidable steel enterprise on the European continent. That pride had hardened into something close to theological doctrine. The 900-ton press was not merely a machine, it was proof that German engineering had surpassed the British model that had dominated global industrial output for 60 years. Proof that the Ruhr Valley, that dense, coal-blackened corridor running east from the Rhine through Essen, Bochum, and Dortmund, was no longer a provincial supplier of raw materials, but the productive center of a new industrial civilization. Proof, most critically, that the men who designed these systems understood forces that ordinary human intuition could not grasp, and therefore could not challenge. This is the central paradox the press presents to history. The same engineering precision that made the 900-ton hydraulic press a legitimate marvel of applied mechanics. The tolerances calculated to the millimeter. The pressure systems engineered to deliver consistent force across thousands of operational cycles. The frame geometry derived from stress analysis that was, for its era, genuinely advanced. Was the identical precision used to justify ignoring what was happening to the men inside the forge hall? The math was immaculate. The human cost was treated as a variable too imprecise to formally calculate. Germany needed rails. This is not a minor point. By 1890, the German rail network had expanded to over 42,000 kilometers, more than doubling in 20 years, and demand was accelerating rather than stabilizing. Every kilometer of track required steel rails produced to increasingly demanding specifications, harder, longer, more uniform, capable of bearing the weight of heavier locomotives on routes that pushed further into mountain and agricultural terrain. The Bessemer process had revolutionized steel production in the 1860s, but shaping that steel, reducing it from rough cast billets into the precise cross-sectional profile a rail required, demanded something that hammers and rolling mills alone could not reliably deliver. It demanded pressure, sustained, enormous, controllable pressure. The hydraulic press provided that. At 900 tons of compressive force, a billet of steel that had been heated to approximately 1,200 degrees Celsius, the precise temperature at which the crystalline structure of the metal becomes temporarily plastic, momentarily willing to be remade, could be reduced to specification in a single controlled stroke. The grain structure of the resulting rail was denser, more uniform, more resistant to the microfractures that cause catastrophic rail failures under repeated load cycling. From an engineering standpoint, the press did not merely shape steel, it improved it at the molecular level. The nation required this. The Krupp Directorate understood this. The Kaiser's government understood this. And so, the question that should have been asked, the question Heinrich Bauer's death in March 1897 should have made unavoidable, was not asked, not formally, not on the record. The internal reports from that period, now partially accessible through the German Federal Industrial Archive in Koblenz, use language so carefully calibrated that the human cost embedded within them is visible only in the margins. Phrases like operational adjustment required at feed station and revised proximity protocols under review appear repeatedly across a 14-month window in which at least 7 workers at the Essen press facility sustained injuries classified by plant physicians as severe. The paradox is this: the machine was celebrated for its precision. Its human consequences were managed through deliberate imprecision of language. A nation was being forged. The press was the instrument. And the men feeding it were, in the accounting of the era, a cost of production, significant enough to require management, insufficiently significant to require truth. That accounting would eventually be challenged, but not before the press had run for another generation, not before the Ruhr Valley had become the industrial spine of a unified German empire, and not before the silence around what happened inside those forge halls had calcified into something that looked, from a sufficient distance, like pride. The machine could not be questioned because the nation it was building could not afford to be questioned. These two facts were, in 1897, treated as identical. They were not. Stand at the eastern rim of the Ruhr Valley in 1850, and what you see is not yet an industrial landscape in the sense the 20th century would come to understand. There are collieries, coal extraction operations working seams that run deep and wet beneath the valley floor. And there are early ironworks, small by later standards, their stacks producing a thin, permanent haze that local farmers had already begun to note in their journals as a new and unwelcome feature of the horizon. The Rhine moves slowly to the west. The roads are unpaved beyond the market towns. What you cannot yet see, standing there in 1850, is what is coming. Germany in the mid-19th century was not a unified nation. It was a constellation of kingdoms, principalities, and free cities bound together in a loose customs union, the Zollverein, that facilitated trade without producing political coherence. Prussia was dominant, but not yet supreme. The question of German unification had been simmering for 2 decades, agitated by liberal nationalists who wanted a parliamentary state and resisted by conservative monarchists who wanted expansion without the inconvenience of popular sovereignty. What neither faction fully anticipated was that the question would ultimately be resolved not by politics, but by industry, specifically by the capacity of the Ruhr Valley to produce steel in quantities that would make Prussian military and economic dominance simply irresistible. The coal was the beginning of everything. The Ruhr sat atop one of the richest coal deposits in Europe, an estimated 220 billion tons of recoverable reserves stretching in seams up to 4 meters thick beneath the valley floor. By 1850, annual extraction was approximately 1.7 million tons. By 1870, it had reached 11.8 million tons. By 1890, the decade in which the great hydraulic presses began appearing in Krupp's Essen complex, it had exceeded 35 million tons per year. This was not gradual growth. This was transformation at geological speed, compressed into a human lifetime, and it reshaped not merely the economics of the region, but its physical geography, its social structure, its air, its water, and the bodies of the men who worked within it. Into this landscape came Alfred Krupp, not the son, Friedrich Alfred, who would preside over the press era, but the father, the original Krupp of industrial legend, the man his workers called Der Kanonenkönig, the Cannon King. Alfred Krupp had taken control of a small steel casting operation in Essen in 1826 at the age of 14, following his father's death, and had spent the next 4 decades transforming it through a combination of technical obsession, commercial ruthlessness, and an almost messianic conviction that steel, specifically Krupp steel, made by Krupp methods, was the material around which the future would be organized. He was not wrong. By 1865, the Krupp works at Essen employed 8,000 men. By 1873, that figure had reached 16,000. By 1890, it was approaching 45,000, a city within a city, with its own hospital, its own housing blocks, its own rules, its own culture, and its own relationship to the concept of loyalty that was simultaneously paternalistic and coercive in ways that no official company document ever acknowledged plainly. Workers at Krupp lived in Krupp housing, bought from Krupp shops, were treated by Krupp physicians, and were buried when the work claimed them, in a manner that the Krupp administrative office considered appropriate. This was the world into which the 900-ton press arrived, but before it arrived, the valley had already been shaped by crisis, specifically by the crisis of scale. The demand for steel rails was accelerating faster than existing production methods could satisfy. Rolling mills, which passed heated billets between successive pairs of shaped rolls to gradually reduce them toward final profile, were productive but inconsistent. The grain structure of rolled rail steel contained directional weaknesses, elongated along the rolling axis, compressed laterally, that made the finished product vulnerable to the specific loading patterns that railway operation imposed. Under repeated axle loading, rolled rails developed transverse fatigue cracks that propagated through the web of the rail section. That's sometimes slowly enough to be caught during inspection, sometimes not. Rail failures were killing people, not in the forge halls, on the tracks. Derailments caused by fractured rails were a documented recurring problem across the German network in the 1870s and 1880s, and the Prussian State Railway Administration, the largest rail operator in Europe, was applying pressure on steel suppliers to improve product reliability in terms that made the commercial stakes entirely clear. Krupp needed a better process. The Ruhr Valley needed a better process. Germany, assembling itself into an empire under Bismarck's directed will, needed a better process. The hydraulic press was the answer the engineers proposed. The scale at which Krupp chose to implement it, 900 tons, a figure that exceeded anything then operating in British or French steel production, was the answer the institution gave to the question of national ambition. The valley had been building toward this machine for 40 years. The coal seams had fed the furnaces. The furnaces had fed the rolling mills. The rolling mills had reached their limit. And now something larger, something that operated by different principles entirely, and something that did not roll steel but compressed it under force sufficient to restructure its internal geometry. That something was being lowered into a pit in the Essen Forge Hall by a crane whose rated capacity it nearly exceeded. The men who would feed it had not yet been told what feeding it would cost. The engineering order that authorized construction of the 900-ton hydraulic press was signed on February 11, 1884, by 3 men: the chief of the Krupp Mechanical Engineering Directorate, the head of the Forge and Press Division, and a Prussian state railway procurement official whose presence at the signing was not accidental. The state was not merely a customer. In the architecture of late 19th century German industrial development, the relationship between Krupp and the Prussian government had become so thoroughly interwoven that distinguishing where one ended and the other began required a forensic patience that neither party particularly encouraged. The press had been preceded by smaller hydraulic installations, 200-ton and 400-ton units that had been operational in the Essen works since the late 1870s. These machines had demonstrated the principle convincingly. Hydraulic compression produced a superior rail, denser grain, tighter cross-section tolerances, measurably better fatigue resistance under cyclic loading. The Prussian Railway Administration's own testing facility at Grunewald had confirmed this in 1881, running a comparative study that subjected hydraulically pressed rails and conventionally rolled rails to simulated axle load cycling at frequencies approximating 10 years of heavy line service. The pressed rails survived, the rolled rails failed first, and they failed in the manner that most concerned the engineers. Not at the surface, where visual inspection might catch deterioration, but internally, through crack propagation that was invisible until it was catastrophic. The case for scaling up was, from a purely engineering standpoint, unanswerable. The question was, how far to scale? The 400-ton press had been the largest hydraulic forging installation in Germany when it was commissioned. The engineers who drew up the preliminary specifications for its successor debated three options: 500 tons, 700 tons, and 900 tons. The 500-ton option was the conservative choice: proven hydraulic cylinder technology, lower infrastructure cost, operational within existing forge hall dimensions. Then the 700-ton option required structural reinforcement of the installation pit, but remained within the envelope of hydraulic technology that Krupp's own engineering staff had direct experience managing. The 900-ton option required everything to be reconsidered from foundation to crown. It required a new pit, excavated to a depth of 8.4 meters below the forge hall floor, lined with reinforced masonry, capable of absorbing the dynamic load of a full compression cycle without transmitting destructive vibration to adjacent structural elements. It required hydraulic cylinders of a bore diameter, 680 millimeters, that Krupp's machine shop had never previously manufactured, operating at working pressures of 315 bar, which placed demands on seal technology and cylinder metallurgy that pushed against the edge of what was reliably achievable in 1884. It required a water accumulator system, essentially a large pressurized reservoir that stored hydraulic energy between press cycles, allowing the ram to be driven downward with consistent force regardless of instantaneous pump output, with a capacity of 14,000 liters, housed in a dedicated accumulator tower that became one of the defining vertical features of the Essen skyline. And it required a frame. The frame was the heart of everything. A hydraulic press of this scale works on a principle of contained opposition. The ram drives downward, the anvil block resists from below, and the frame, the structural columns and crossheads that connect these two elements, must absorb the entire compressive load without deflecting beyond the tolerances that precision forming requires. At 900 tons, the tensile stress in the main tie rods of the frame during a full compression cycle reaches values that, in 1884, could only be accommodated by steel of a quality that Krupp was, conveniently, the primary producer of in Germany. This was not a coincidence. The press specification had been written, in part, around the properties of Krupp's own best-grade forged steel, creating a machine that only Krupp could build, or into a specification that demonstrated Krupp's superiority, to produce a product that the state had already agreed to purchase. The circularity was elegant. It was also deliberate. Construction of the press took 31 months. The installation crew, 340 men at peak, worked in 3 shifts to maintain continuity, because the forge hall could not be taken fully offline during a construction period of that length, without disrupting production commitments to the Prussian Railway Administration. This meant that the new press pit was being excavated, lined, and gradually fitted with its lower assembly, while adjacent presses continued operating, a condition that the installation engineers later noted in internal memoranda on created hazardous proximity between construction workers and operational equipment at multiple points during the project. Those memoranda were filed. They did not produce operational changes. The press was commissioned on September 17, 1886. The Krupp administrative record of that day describes a formal ceremony attended by Friedrich Alfred Krupp, senior engineers, state railway officials, and a delegation from the Prussian War Ministry, whose interest in the press derived from its secondary application, not rails, but armor plate. A machine that could compress rail steel could compress armor plate steel. A machine that improved rail integrity could improve the ballistic resistance of the steel plate being fitted to the new generation of warships that Wilhelmina Germany was beginning to conceptualize. The press was, from its first operational day, simultaneously a civilian and a military instrument. This duality would shape everything that followed, including the decisions made about safety, about worker protection, and about what could and could not be publicly acknowledged when men began to die. On September 17, 1886, none of that was spoken of. Friedrich Alfred Krupp stood before the assembled dignitaries in the forge hall, the heat from 3 adjacent furnaces radiating through the space, the smell of hot scale and hydraulic oil hanging in the air, the accumulator tower visible through the high industrial windows, and declared the press a monument to German technical achievement. The first billet was fed into position by a worker whose name the administrative record does not preserve. The ram descended. The nation's spine was being built, one compressed rail at a time, and the men guiding the steel into position would learn, across the years that followed, exactly what it cost to stand that close to a monument. Numbers at industrial scale lose their meaning quickly. They become abstractions, figures in a procurement document, entries in an engineering log, data points in a stress analysis table that only specialists can interpret. 900 tons is a number of that kind. It appears in Krupp's operational records with the same typographic weight as any other specification, sandwiched between hydraulic pressure ratings and cycle time targets, and it requires a deliberate act of translation to understand what it actually represents in physical terms. Let's begin with this. The compressive force delivered by the Essen press at full stroke, 900 metric tons, or approximately 8.8 million newtons, is equivalent to the combined weight of 600 fully loaded railway freight wagons pressing down onto an area roughly the size of a dining table. It is the force required to deform structural steel, not by cutting or grinding or gradual rolling attrition, but by overwhelming the metal's own internal resistance, by exceeding the yield strength of the material so completely that its crystalline lattice restructures under the load, the grains elongating and reorienting in patterns determined by the die geometry rather than by the steel's prior history. This is not shaping in the conventional sense. This is closer to a controlled form of destruction, followed immediately by enforced reconstruction. The billet entering the press had been heated in a coal-fired furnace to between 1,150 and 1,250 degrees Celsius, a range maintained within tight limits because temperature directly governed the steel's plastic behavior. Too cold, and the material resisted the press with enough residual strength to cause die damage or, worse, unpredictable lateral displacement under load. Too hot, and the surface oxidized aggressively, forming thick scale that contaminated the die face and produced surface defects in the finished rail that required costly secondary grinding. The window of correct temperature was approximately 40 seconds wide from the moment the billet left the furnace mouth to the moment the ram made contact. 40 seconds. In that window, the billet had to travel from furnace to feed station, be positioned precisely on the lower die, and be cleared of personnel before the ram descended. The men doing this work were not operating at the edge of human capability in terms of strength. The tongs and mechanical assists made the physical handling manageable. They were operating at the edge of something else, the margin between the speed required by the production cycle and the space required for safe withdrawal. At full production tempo, which the Krupp Forge management defined as 18 compression cycles per hour, a billet was entering the press space every 3.3 minutes. Each cycle required furnace extraction, transfer, positioning, operator withdrawal, compression, die opening, and removal of the finished blank. Each step consumed time, each step consumed space, and the press pit geometry, the configuration of the lower die, the feed approach path, the ram's operational arc, and the clearance dimensions around the feed station had been designed to accommodate the process at rated tempo with what the engineering specification described as adequate operational margin. What adequate meant in practice was a clearance of approximately 0.9 meters between the edge of the feed station operator's working position and the outer boundary of the ram's descending path. Less than 1 meter. At full compression speed, the ram traveled its full stroke in approximately 4.3 seconds. The hydraulic system driving the ram operated through a sequence of valve actions. The inlet valve admitting pressurized water from the accumulator, the ram descending under load, the exhaust valve opening to allow return stroke. In normal operation, this sequence was initiated by the press operator, a separate individual from the feed station worker, positioned at a control station set back from the press pit, on a signal from the feed station that the billet was positioned and personnel were clear. The signal system in 1886 was a hand gesture. By 1891, it had been upgraded to a bell pull. Neither system provided any mechanical interlock between personnel clearance and valve actuation. The ram would descend when the press operator opened the inlet valve. Whether anyone remained within its operational arc at that moment was a function of human communication, human attention, and the 0.9-meter clearance that the engineering specification had deemed adequate. This was the gap, not merely physical but conceptual, between what the machine required and what the safety architecture provided. The press had been engineered with extraordinary precision at the level of hydraulic performance, pressure ratings calculated to 3 significant figures, frame stress analysis conducted to standards that were genuinely advanced for the period, cylinder metallurgy specified with an attention to material quality that reflected Krupp's best capability. The interface between the machine and the human body, the last half-meter of space, the signal system, the withdrawal time available within the production cycle, had been treated as an operational matter rather than an engineering matter. Operational matters were managed by foremen. Foremen were evaluated on output. Output was measured in cycles per hour. There was one further engineering reality that the press imposed on its environment, one that the operational records acknowledge only obliquely, but that former workers described with consistency in the labor testimony records compiled by the German Metal Workers Union between 1899 and 1903. The press, at full compression, transmitted a pressure wave through the forge hall floor that was measurable at a distance of 40 meters. Closer in, within 10 meters of the pit, the vibration was not merely measurable, but physically present in a way that affected equilibrium. Men who worked the feed station for extended periods reported that their spatial judgment, their ability to accurately perceive distance and position, degraded over the course of a shift. The tremor in the left hand that engineers had noted clinically was a symptom of a broader neurological accommodation to chronic vibration exposure that no one in 1886 and very few people in 1897 had a physiological framework to accurately describe. The machine did not merely demand precision from the men who served it, it progressively compromised their capacity to be precise. This fact appears nowhere in the Krupp Engineering Directorate's operational specifications. It appears in the union testimony records, in the handwritten margins of shift foremen's logs, and in the medical notes of the Krupp Company physician, Dr. Ewald Schmitter, who between 1889 and 1896 recorded 37 consultations with press hall workers describing symptoms he catalogued under the general heading of Erschütterungsschäden, vibration damage. Without ever formally connecting those symptoms to the operational safety question that they directly and urgently implied, the machine was precise. The men were becoming less so. The production schedule did not change. On the 14th of June, 1893, a junior hydraulic engineer named Wilhelm Dressler submitted a 6-page internal report to the Krupp Forge Division management. The report was titled, in the careful bureaucratic language of the era, Bemerkung zur Betriebssicherheit der Großpresse, Halle 7, Observations on the Operational Safety of the Large Press, Hall 7. It was received, logged, assigned a reference number, and filed in the Forge Division Administrative Registry. No formal response to its contents appears in the surviving record. No operational changes attributable to its recommendations were implemented in 1893, or in 1894, or in 1895. Wilhelm Dressler's report was not, by any measure, a radical document. It did not call for the press to be shut down. It did not use language that could be characterized as alarmist. It was, in tone and structure, the kind of carefully modulated technical memorandum that a junior engineer produces when he has identified something that concerns him, but is acutely aware that the institution he serves does not welcome concern that implies operational change. What it said, in the measured technical language of its 6 pages, was that 3 specific conditions at the press installation had developed characteristics that fell outside the parameters the original engineering specification had defined as acceptable. The first condition was seal degradation in the primary hydraulic cylinders. The cylinder seals, leather cup seals of a type standard for the era, had been specified with a replacement interval of 2,000 operational cycles. By June 1893, the press had completed approximately 47,000 cycles since commissioning, and maintenance records indicated that seal replacements had been performed at intervals averaging 3,400 cycles, rather than the specified 2,000. The reason, which Dressler noted without editorial comment, was that seal replacement required a full press shutdown of approximately 14 hours, and press shutdowns disrupted the production schedule in ways that forge management was reluctant to authorize without compelling cause. Worn seals produced measurable hydraulic leakage. Dressler had personally measured leakage rates at the cylinder crown that indicated seal efficiency had fallen to approximately 91% of design specification. At 91% efficiency, the press was still functioning. But the margin between functioning and not functioning had narrowed, and the failure mode of a hydraulic seal under sustained overservice was not gradual further degradation. It was rupture. A ruptured high-pressure hydraulic seal on a cylinder operating at 315 bar released pressurized water with a force that Dressler calculated, in the appendix of his report, would project fluid and seal fragments across a radius of approximately 4 meters at velocities sufficient to cause severe laceration injuries. The feed station was 1.1 meters from the primary cylinder crown. The second condition Dressler identified was fatigue cracking in the lower die block mounting assembly, specifically in the 4 forged steel brackets that located the lower die on the press table, and resisted the lateral forces generated when a billet was not perfectly centered at the moment of compression. Imperfect centering was, Dressler noted, not an exceptional occurrence. At the production tempo the forge management required, perfect centering on every cycle was not reliably achievable. The lateral forces generated by off-center compression were within the original design envelope individually, but their cumulative effect on the bracket material, the progressive growth of microcracks under repeated asymmetric loading, was a phenomenon that the original stress analysis had not fully accounted for. It is because fracture mechanics as a formal engineering discipline was, in 1884, still in its theoretical infancy. By 1893, Dressler had measured crack propagation in 2 of the 4 brackets using a technique of his own devising, applying a thin coat of lime wash to the bracket surface, allowing it to dry, and then running the press through 10 cycles and examining the lime surface for crack-following fracture lines. What he found suggested that the cracks in the most affected bracket had reached a depth of approximately 8 millimeters into a section whose full thickness was 60 millimeters. This was not immediately critical, but the growth rate he estimated from comparative measurements taken 6 months apart suggested that without intervention, the crack would reach a structurally significant depth within 2 to 3 years. A failed die mounting bracket under full compression load would not merely crack, it would displace. The lower die, suddenly freed from lateral constraint on one side, would rotate under the compressive load, not dramatically, but enough to redirect the force vector of the compression cycle laterally rather than vertically, enough to project the billet being compressed, a mass of approximately 180 kilograms of steel at 1,200 degrees Celsius, out of the press throat and across the forge hall floor. The feed station operator would be in that trajectory. The third condition in Dressler's report was the most abstract and, in retrospect, the most damning. He had observed, and documented with a methodical care, that suggests he understood he might be writing for a future audience that the present one would not constitute, that the production tempo demanded by forge management had progressively increased since commissioning. The original operational specification had rated the press at a maximum of 15 compression cycles per hour, a figure derived from an analysis of the time required to safely execute each step of the feed, compress, and remove sequence. By June 1893, the forge management's production target had been raised in 3 incremental steps to 18 cycles per hour. The operational specification had not been revised. The safety analysis underlying the original cycle rate had not been revisited. The 3 additional cycles per hour had been absorbed, in practice, by reducing the time allocated to the feed station withdrawal sequence, the step during which the operator moved from billet positioned to clear of press arc. The withdrawal time built into the original 15-cycle rate was 8.2 seconds. At 18 cycles per hour, the time available for the same movement was 6.1 seconds. Dressler did not editorialize. He recorded the numbers. He noted that the reduction in withdrawal time had not been accompanied by any modification to the press pit geometry, the signal system, or the operational protocol. He noted that the 0.9-meter clearance between the feed station position and the ram's operational arc remained unchanged. He noted, in his final paragraph, that the combination of reduced withdrawal time, degraded seal condition, and die bracket fatigue cracking represented, in his professional assessment, a compound risk profile that warranted formal review by the engineering directorate. He signed the report. He submitted it. He received, as far as the surviving record shows, no reply. 3 years and 9 months later, Heinrich Bauer arrived 7 minutes early for his shift, checked the pressure gauge out of ingrained habit, and took his position at the feed station. The brackets Dressler had measured in 1893 had continued to develop. The seals had continued to wear. The production tempo had not decreased. And the report that might have changed the sequence of what followed on March 4, 1897, sat in the Forge Division Administrative Registry, correctly filed, correctly referenced, and entirely unacted upon. Some silences in industrial history are accidental. This one had a reference number. They were not, by the standards of the Ruhr Valley labor market in the 1890s, poorly paid. This is the first thing to understand about the men who worked the feed stations of the Essen Hydraulic Press Hall, because it explains, at least partially, why they stayed, why they absorbed conditions that their bodies registered as damage long before their minds framed them as injustice, and why the institutional silence around those conditions was so durable for so long. A press hall feed station worker at Krupp in 1895 earned between 32 and 38 marks per week, depending on seniority and shift allocation. A construction laborer in Essen earned approximately 18 marks per week. A textile worker in the Rhine Valley earned 14. The differential was not incidental. It was structural. A deliberate feature of the Krupp wage architecture that tied higher pay to the most physically demanding and hazardous roles, creating a financial logic that made dangerous work feel like a reward rather than a liability. Heinrich Bauer earned 36 marks per week. He had a wife, Margareta, and 2 daughters, Elsa, 7, and Hannah, 4. They lived in a Krupp housing block on Altendorfer Strasse, 3 rooms and a kitchen, with access to the communal courtyard and the company water pump. The rent was deducted directly from Bauer's wage packet. The company physician, Dr. Schmitter, treated the family's medical needs at reduced cost. Elsa attended the Krupp Workers' School, where the curriculum included, alongside arithmetic and reading, a formal component that Krupp's administrative literature described as Werkstreue, fidelity to the works, a conceptual orientation toward the company as a form of benevolent authority to which gratitude and loyalty were the appropriate responses. This was the architecture of dependency that Alfred Krupp had designed and Friedrich Alfred Krupp had refined. It was not experienced by those within it as oppression, or at least not consistently, not simply. It was experienced as a form of stability in a world where stability was not abundant, offered by an institution that was simultaneously employer, landlord, physician, educator, and, for the men who had worked there long enough, something approaching the primary framework of identity. To leave Krupp was not merely to change employers. It was to dismantle an entire structure of life and begin again from nothing in a labor market that offered worse pay and no safety net. Most men did not leave. Most men accommodated. Georg Winkel had worked the feed station for 7 years. By 1895, he was 29, unmarried, and had developed the particular physical vocabulary of the long-term press worker, a slight forward lean at the shoulders from years of bending to the feed position. The chronic left-hand tremor that Dr. Schmitter had documented in his consultation records, and a specific kind of attentional acuity, a constant peripheral awareness of the press ram's position, that former workers described in union testimony as becoming involuntary after the first year. You stopped choosing to watch the ram. You simply always knew where it was. Your nervous system made the calculation without consulting you. Winkel had seen 2 accidents at the press before 1895. The first, in 1891, had cost a man named Peterson the 3 middle fingers of his right hand when a billet shifted laterally during positioning, and Peterson, instinctively trying to correct the shift, had not completed his withdrawal before the signal was given and the ram descended. The second, in 1893, had been a hydraulic seal failure. Not the catastrophic rupture Dressler had calculated as a possibility, but a partial failure. A sudden lateral jet of pressurized water at approximately 280 bar that had struck a worker named Haas across the left side of his face and chest, causing burns and lacerations that Dr. Schmitter's records classified as severe but not permanently disabling. Both incidents had been investigated by Forge management, and both investigations had produced the same category of finding: operator error or unavoidable equipment wear, addressed through revised protocols that were, in practice, indistinguishable from the protocols they replaced. Neither investigation referenced Dressler's 1893 report. Neither investigation produced a reduction in the production cycle rate. What they produced was a ritual. After each accident, the Forge foreman would gather the press crew for what was called a Sicherheitsbesprechung, a safety discussion, during which the incident was described, its cause attributed to a specific failure of procedure or attention, and the correct procedure was restated. The men listened. They had no formal mechanism to do otherwise. The Krupp Works did not permit union organization. Alfred Krupp had suppressed 2 early unionization attempts in the 1870s, with a combination of dismissals and a formal declaration that the company's own welfare provisions made external labor representation unnecessary. The Werkstreue curriculum in the company school had, across a generation, produced workers who understood, at a level below articulate political thought, many that collective challenge to management authority was a form of ingratitude toward an institution that had given them everything they had. And yet, the men talked. In the housing blocks, in the Krupp-operated canteen on Kronprinzenstrasse, in the low voices of a shared shift, walk across the Forge yard at 5 in the morning, they talked about the press in a register that the official record never captured. Georg Winkel told his sister in a letter dated November 1894, a letter that survived in a family archive and was later cited in the 1901 Metalworkers Union Report on Ruhr Valley industrial conditions, that working the feed station felt, after enough years, like being in a conversation with something that did not know you were there. The machine did not see you. The machine did not adjust for you. You adjusted for it, every cycle, every shift, every year, and the adjustment was total, physical, neurological, and psychological, and it accumulated in the body in ways that did not reverse when the shift ended. He wrote, "The press does not hate us. That would be easier. It simply does not know we exist." The men who fed the press understood, with the precision of long experience, exactly what the engineering reports expressed in technical abstraction, that the machine and the human being occupying the same space were operating on incommensurable terms, that the machine's requirements and the human body's limitations had been brought into proximity by institutional decision and held there by institutional inertia, and that the distance between adequate and catastrophic was, in that forge hall, measured in seconds and centimeters. They understood this. They came back, shift after shift, because the alternative, 18 marks a week and no housing, no physician, no school for the children, was not a real alternative. They came back because the tremor in their left hand had not yet become an inability to work. They came back because Peterson had lost 3 fingers and was still employed, and Haas had been burned and was still employed, and the institution that had placed them in proximity to the machine was the same institution that would care for them if the machine finally made its indifference definitive. They came back because Heinrich Bauer came back every morning, 7 minutes early, and checked the pressure gauge, and took his position, and the ram descended, and the rail was made, and the nation's tracks extended another meter further into the future that the machine was building. Until the morning, it didn't. The morning shift at Hall 7 began at 6 a.m. By 6:45, the furnaces had reached operating temperature, and the first billets of the day were in the heating chambers, their surfaces beginning the slow transition from dull red to the bright orange-white that indicated proximity to the working temperature range. The accumulator tower had been pressurized during the pre-shift preparation cycle. The press operator that morning was a man named Franz Kellner, 44 years old, 17 years at the Krupp Works, 8 of them at this specific press. Georg Winkel was on the feed station. Heinrich Bauer was his relief, scheduled to rotate into the feed position at the 8 a.m. crew exchange. At 7:52 a.m., Winkel completed what the shift log recorded as cycle 31 of the morning's production run. The billet had positioned cleanly, the signal had been given, the ram had descended, compressed, and returned. The finished blank had been extracted by the removal crew. The shift log, maintained by the forge foreman Carl Stein, records the cycle time as within tolerance and makes no note of any anomaly. At 7:58 a.m., Bauer took the feed station position from Winkle, standard rotation. Winkle moved to the removal station on the opposite side of the press pit. Bauer pulled on his leather apron, checked the pressure gauge on the south column, 308 bar within the operating range, and positioned himself for cycle 32. What happened during cycle 32 was reconstructed afterward from the testimony of 11 witnesses, the physical evidence examined by the Krupp Engineering Directorate's accident investigation team, and the medical findings of Dr. Schmitter, who arrived at the press hall at approximately 10:55 a.m. The record is imprecise on the exact time, and whose clinical notes from that day represent the most direct surviving account of what the press had done. The billet for cycle 32 was extracted from the furnace at 7:59 a.m. and carried to the feed station by Bauer using the standard tong assembly. Witness testimony agrees that the billet appeared to be correctly positioned on the lower die. Bauer signaled clearance to Kellner at the control station. Kellner opened the inlet valve. What happened next took approximately 1.8 seconds. The lower die block, in the first fraction of a second of ram contact with the billet, displaced laterally. The crack propagation that Dressler had measured in 1893 in the northeast bracket of the die mounting assembly had, in the intervening 3 years and 9 months, advanced from 8 millimeters to what the post-incident examination measured as 31 millimeters, past the critical threshold at which the remaining intact material could resist the lateral force component of an off-center compression event. The billet for cycle 32 was not perfectly centered. It was off-center by approximately 22 millimeters, a deviation within the range that the feed station crew produced regularly at the production's tempo the forge management required. At 22 millimeters off-center, with a northeast bracket whose remaining intact section was insufficient to resist the resulting lateral force, the die block rotated. The rotation was 4.3 degrees, 4 degrees, less than the angle of a gentle slope, less than the deviation that the human eye can reliably detect in a static surface. In 1.8 seconds, under 900 tons of compressive force, 4.3 degrees was enough to redirect the billet's displacement vector from vertical to lateral. The billet, 180 kilograms of steel at approximately 1,180 degrees Celsius, exited the press throat in a lateral trajectory and traveled 2.3 meters across the forge hall floor before striking the base of the south column housing. Heinrich Bauer was in that trajectory. He had completed his withdrawal movement. He was, and this is the detail that the accident investigation report records with a precision that reads, in retrospect, as almost unbearable, within the clearance envelope that the operational specification defined as safe. He was 0.94 meters from the ram's operational arc. He was, by the specification's own standard, in a position that should not have been lethal. The specification had not accounted for a die block rotating 4.3 degrees. Dr. Schmitter's clinical notes record thermal injury covering approximately 60% of Bauer's body surface area, consistent with direct contact with or near proximity to a mass of steel at the recorded temperature. The notes also record blunt force trauma to the left side of the thorax and the left arm, consistent with the physical displacement that the billet's lateral movement would have caused. Schmitter's final entry on the case is dated March 4, 1897, timed at 11:23 a.m. Heinrich Bauer died at 11:23 a.m. He had been conscious for portions of the intervening time. The testimony records do not elaborate on what he said, if anything. Georg Winkel, who was at the removal station on the opposite side of the press pit and witnessed the event, did not return to work at the press hall. The shift log for March 4th, BOA 1897 records production, resuming at 2:15 p.m., following inspection of the press by the Engineering Directorate team and replacement of the failed die mounting bracket. The press resumed operation the same afternoon. This fact, that the machine was running again within hours of the death of the man who had served it that morning, is recorded in the shift log without comment. It was not an oversight. It was institutional reflex, the production imperative expressing itself with a consistency that required no deliberate decision by any individual. The rails were needed. The press made the rails. The press was repaired. The press ran. What followed March 4th, 1897, was not silence exactly. It was something more controlled than silence, a managed response that addressed the surface facts of the incident while protecting the institutional architecture that had produced them. The Krupp Engineering Directorate conducted its internal investigation within 10 days. Its findings attributed the accident to bracket fatigue in excess of anticipated wear rates, a finding that was accurate as far as it went, and carefully constructed to go no further. The investigation report did not reference Dressler's 1893 memorandum. It did not examine the production cycle rate increase. It did not address the signal system, the withdrawal time reduction, or the compound risk profile that Dressler had formally documented 4 years earlier. It recommended enhanced inspection intervals for die mounting components and improved billet centering protocols. The German Metal Workers Union, the Deutscher Metallarbeiter Verband, which had been organizing in the Ruhr Valley despite Krupp's resistance and which had, by 1897, established sufficient presence to function as a channel for worker testimony, received accounts of the March 4th incident from multiple Krupp workers within weeks. The accounts were detailed, consistent, and significantly more complete than the Engineering Directorate's official findings. They described the bracket cracking that workers had observed and mentioned to foremen without formal response. They described the acceleration of the production cycle rate. They described the reduction in withdrawal time. They described Dressler's report, not by name, because the workers did not know Dressler's name or the report's reference number, but by its substance. That's because what Dressler had observed and documented in 1893 was what the workers had experienced and discussed among themselves for years. The Union compiled these accounts into a formal submission to the Prussian Factory Inspectorate in August 1897, requesting investigation of safety conditions at the Krupp Essen Press Hall. The Factory Inspectorate acknowledged receipt. An inspector visited the Essen Works in October 1897. His report, filed in November, noted that conditions at the press hall appeared to meet the general requirements of the applicable industrial safety regulations. Regulations that had been written in 1878 and had not been substantively revised to account for the specific hazard characteristics of hydraulic press technology at the scale Krupp was now operating. Margareta Bauer received a death benefit payment from the Krupp Workers' Welfare Fund of 240 marks, approximately 7 weeks of her husband's salary. She and her daughters remained in the Altendorfer Strasse housing block for 14 months, until the terms of the Krupp housing agreement required that the dwelling be vacated following the death of the employed worker whose wage had underwritten the tenancy. She then moved to a rented room in Bochum, where a cousin could provide some measure of support. Elsa and Hannah Bauer did not return to the Krupp Workers' School. The press ran, the rails were made, the nation's tracks extended further. And in the Forge Hall on Altendorfer Strasse, a detail of geography that may or may not have been noticed by anyone in the directorate, Heinrich Bauer's replacement took the feed station position for cycle 33, and the shift log for the following week records production at full tempo, 18 cycles per hour, every hour of every shift, without interruption. In 1900, 3 years after Heinrich Bauer's death, Germany surpassed Great Britain in annual steel production for the first time. The figure, 6.6 million tons of finished steel against Britain's 4.9 million, was celebrated in the German industrial press with a fervor that had the character of a territorial conquest, which in economic terms it effectively was. The Ruhr Valley's presses, furnaces, and rolling mills had accomplished something that 50 years of British industrial dominance had made seem structurally impossible. They had broken the monopoly of the nation that had invented industrial capitalism and replaced it with a new center of gravity. The 900-ton press at Essen had contributed to every meter of rail in that achievement. It had also contributed to something the celebration did not mention. Between 1886 and 1905, the press's first 2 decades of operation, the Krupp Company physicians' records, cross-referenced with the Forge Division shift logs and the Metal Workers Union testimony archive compiled between 1899 and 1906, allow a partial reconstruction of the human cost of the press hall's output. Partial because the record-keeping was designed, whether consciously or by institutional convention, to disperse and minimize rather than to aggregate and confront. Injuries were recorded by physician, by foreman, and by the welfare fund administrator. 3 separate record streams that used different classification systems and were never formally consolidated. Deaths were recorded differently again, by category and by cause. In language that consistently attributed outcomes to proximate mechanical failure, rather than to the systemic conditions that had created the environment in which mechanical failure was lethal. What the cross-referenced record yields, with the caveats appropriate to incomplete documentation, is this. In the press hall's first 20 years, at least 11 workers died of injuries directly attributable to press operations. A further 43 sustained injuries classified as severe, meaning injuries that resulted in permanent disability, loss of limb function, or extended incapacity of 6 weeks or more. An unknown additional number, sustained injuries classified as minor, that the physician's records suggest were, in several documented cases, more accurately described as severe injuries managed conservatively to avoid triggering the welfare fund's higher-tier compensation obligations. 11 deaths, 43 severe injuries. A machine celebrated as a monument to German technical achievement. The systemic consequence of these facts was not reform. It was refinement, a careful recalibration of the institutional response to industrial harm that preserved the production architecture while creating enough visible attention to safety to satisfy the regulatory framework and quiet the most persistent union complaints. After March 1897, the Krupp Engineering Directorate did implement enhanced component inspection intervals, a mechanical interlock between the feed station clearance signal and the press control valve, the single change that would have most directly addressed the human safety gap Dressler had identified, was studied in 1898 and rejected on the grounds of cycle time impact. The study estimated that a properly designed interlock system would add 4.1 seconds to each compression cycle, and reducing throughput from 18 to approximately 16 cycles per hour. The Directorate's memorandum rejecting the interlock recommendation notes, without apparent awareness of its implications, that the 2-cycle reduction would cost the Forge division approximately 340 marks per shift in output value. Heinrich Bauer's weekly wage had been 36 marks. The interlock that might have kept him alive was rejected because its cost, per shift, was equivalent to the wages of 9 workers for a week. The union's response to the post-1897 period was constrained by the same institutional architecture that had shaped the workers' individual responses. The Krupp system of housing, welfare, and schooling made collective action genuinely costly in ways that went beyond the economic. To strike was to risk the housing. To publicly agitate was to risk the physician. To send children to union meetings rather than the company school was a statement about loyalty that the Krupp administrative apparatus had been designed across 2 generations to make feel like a statement about ingratitude. Nevertheless, the Metal Workers' Union persisted. The August 1897 submission to the Factory Inspectorate was followed by a second submission in 1899, a third in 1901, and a formal petition to the Reichstag Labor Committee in 1903 that named the Krupp Essen Press Hall specifically and cited the 11 deaths by name, date, and cause. The petition requested revision of the 1878 Industrial Safety Regulations to include hydraulic press-specific provisions, mandatory interlocks, minimum clearance standards recalculated for actual rather than theoretical production tempos, mandatory reporting of all press-related injuries to the Factory Inspectorate rather than solely to company physicians. The Reichstag Labor Committee received the petition. It was referred to a subcommittee. The subcommittee consulted with representatives of the German steel industry, a consultation process in which Krupp's legal and administrative directorate participated actively. The subcommittee's report, issued in 1905, recommended voluntary adoption of enhanced safety guidelines by press operators, expressed confidence in the existing inspection regime, and declined to propose mandatory regulatory revision. This outcome was not the product of indifference. It was the product of a structural relationship between industrial capital and the German state that the press itself embodied. The machine that was building Germany's rail network, armor plating Germany's warships, and establishing Germany's industrial supremacy over Britain was not, in the political calculus of the Wilhelmina Empire, meant a subject on which the state was inclined to impose constraints that the industry characterized as economically damaging. The Krupp works were not merely a company, they were an instrument of national policy. Bismarck had understood this. Wilhelm II understood it more emphatically still. His relationship with Friedrich Alfred Krupp was one of mutual dependence barely disguised as patronage. To challenge the press hall's safety conditions was, in the political language of the era, to challenge the institution upon which German military and industrial power rested. The Union men who submitted their petitions understood this perfectly. They submitted them anyway, because the alternative was to accept a silence that the 11 dead and 43 severely injured had not chosen. But the silence held. It held because the nation the press was building required it to hold, or at least that was the institutional logic, repeated in enough memoranda and committee reports and regulatory findings to acquire the durability of received truth. The silence held because the production schedule required it to hold. The silence held because 340 marks per shift required it to hold. And outside the forge hall, the rails the press had made extended across the landscape in every direction, into the agricultural east, into the industrial west, into the mountain passes of the south, stitching together a nation that moved faster, carried more, and reached further than anything the previous century had imagined possible. The rails did not record the names of the men who had made them. The tracks did not carry that history. As the trains that ran on Krupp steel moved through a landscape that had been built, in part, on a silence carefully maintained by institutions whose interests were served by maintaining it. The nation that rode those rails knew the press had built them. It did not know, and was not encouraged to ask, what the press had consumed to do so. The 900-ton hydraulic press at Krupp's Essen Works operated until 1931. By that year, it had completed an estimated 1.4 million compression cycles, a figure derived from production records that are incomplete for the war years, but sufficiently detailed for the periods before and after to support reasonable interpolation. It had shaped steel that became rail across every major German rail corridor. It had shaped steel that became armor plate on warships that fought at Jutland and Dogger Bank. It had shaped steel that became, during the First World War, components of artillery systems whose projectiles killed men in the same industrial quantities that the press had been quietly killing men in Essen since 1886, though those deaths were celebrated as sacrifice rather than managed as production cost. In 1931, the press was decommissioned, not because it had failed and not because safety concerns had finally overcome institutional inertia, but because the technology had moved forward. A new generation of hydraulic presses, operating at 2,500 tons and above, had made the 900-ton machine obsolete in the same way the 900-ton machine had made rolling mills inadequate 40 years earlier. The forge hall was reconfigured, the press pit was filled. The accumulator tower, that defining vertical feature of the Essen skyline that workers in the housing blocks of Altendorfer Strasse had been able to see from their windows, was demolished in 1933. The physical machine ceased to exist. The institutional knowledge it had generated about hydraulic press technology, about steel grain structure, or about the relationship between compressive force and material performance, survived and propagated through the German engineering tradition, informing the design of the larger presses that replaced it, and, through those presses, the still larger installations that defined post-war German industrial reconstruction. What did not propagate through any formal institutional channel was the knowledge about what the machine had cost the men who served it. That knowledge survived differently, in Union archives, in pension records, in the medical literature that the Erschütterungsschäden consultations had begun to generate, and in the specific and private form of family memory. Elsa Bauer, Heinrich Bauer's elder daughter, 7 years old when her father died, lived until 1962. In the 1950s, when the Federal Republic of Germany began a formal process of industrial and historical documentation as part of its broader project of post-war institutional reconstruction, she was interviewed twice. Once by a researcher from the University of Bochum documenting Ruhr Valley labor history, and once by a journalist from a Düsseldorf newspaper working on a retrospective about Krupp's industrial legacy. Both interviews cover the same territory: her memories of Altendorfer Strasse, her father's routines, the morning of March 4th, 1897, the afternoon when the housing office notification arrived, the move to Bochum. In the Bochum interview, she described something that the researcher noted and the published account preserved. She said that for years after her father's death, whenever she heard machinery, any machinery, the sound of a factory, a construction site, a large engine, she felt what she described as a physical pressure in her chest. Not grief exactly, she said, something more structural than grief. The sense that something very large was pressing down, and that the space available to breathe was precisely calculated to be sufficient and no more. She had never worked in a factory. She had never seen the press. The pressure she was describing was the one her father had lived inside for 11 years, transmitted to her not through experience, but through the specific shape of his absence. Wilhelm Dressler, the junior engineer whose 1893 report had documented the compound risk profile of the press installation with a precision that the institution had chosen not to act upon, left Krupp's employ in 1899, 2 years after Bauer's death. The available record does not indicate whether his departure was voluntary or managed. He worked subsequently for a municipal waterworks engineering office in Cologne, designing hydraulic distribution systems for domestic water supply, a professional pivot that placed him in the same technical domain as the press, but in a context where the hydraulic forces involved were orders of magnitude smaller, and the human proximity to pressurized systems was governed by regulations that his own experience had perhaps taught him to value. He retired in 1921 and died in 1934. His 1893 report, if filed correctly in the Krupp Administrative Registry, survived the Second World War in the Krupp Company archive, and was identified by researchers in the 1970s as part of a broader project examining the history of industrial safety documentation in German manufacturing. When the researchers read it, they noted that its findings had anticipated the conditions of Heinrich Bauer's death with an accuracy that, had the report been acted upon, might have prevented that death with a degree of confidence sufficient to classify as certainty rather than probability. They noted this in the academic literature. The academic literature was read by specialists. The specialists cited it in subsequent work. The knowledge, 40 years after Dressler's death and 70 years after his report, it finally circulated through the institutional channels that had been closed to it in 1893. This is the particular cruelty of industrial historical memory. It arrives with full accuracy and complete detail at the precise moment when it can no longer protect anyone. The legacy of the 900-ton press is therefore double, and the two halves of it do not resolve into a unified narrative no matter how long you look at them. On one side, an engineering achievement of genuine significance, a contribution to the material infrastructure of a modern nation that is measurable in kilometers of track, in the structural integrity of bridges and rolling stock, in the industrial capacity that made Germany a major power in the 20th century's first decades. These things are real. The press made them. The engineering was extraordinary for its era, and the knowledge it generated advanced the discipline of applied mechanics in ways that did not disappear when the machine was decommissioned. On the other side, 11 men dead, 43 severely injured, a report filed and ignored, an interlock rejected for 340 marks per shift. A widow given 240 marks in 14 months before the housing notice arrived, 2 small girls moved to Bochum, and a silence maintained by the combined weight of institutional interest, regulatory inadequacy, and a national narrative about industrial progress that had no formal language for what the press consumed in the process of producing what it produced. Georg Winkel, who had stood at the removal station on the opposite side of the press pit and watched Cycle 32 on the morning of March 4, 1897, never returned to press hall work. He transferred within the Krupp works to a position in the rail finishing department, where the steel arrived already shaped, and the work involved grinding and inspection, rather than feeding billets into a machine that did not know he existed. He worked there until 1912. When the tremor in his left hand had advanced sufficiently that the precision required for inspection work was no longer reliably achievable. He was retired on a reduced Krupp pension and moved to a smaller room in the Essen Workers' Quarter. In 1901, he had been one of the workers interviewed by the Metal Workers Union for its testimony compilation. That his account of the March 4th incident was detailed, precise, and entirely consistent with the physical evidence. He described Bauer's positioning at the feed station. He described the billet going in. He described the sound, not the sound of the compression itself, which was the sound he had heard thousands of times, and which his nervous system had long since learned to categorize as normal, but a different sound, a lateral sound, something that arrived from the wrong direction, and then the heat, the sudden heat across the left side of his face from 15 meters away, and then the silence that followed, which he said was the loudest silence he had ever heard. He said, "The press did not stop. That is what I remember most clearly. After everything, the press did not stop. We stopped. The press was already ready for the next cycle." That detail, the machine's indifference, its readiness, its absolute continuity, is the detail that carries the full weight of what the 900-ton press represents in industrial history. Not the engineering achievement, though the achievement was real. Not the deaths, though the deaths were real and their causes were documented and preventable. The detail that carries the weight is the readiness. The machine was always ready for the next cycle. The production schedule did not include a unit of time corresponding to human grief or human reckoning, or the pause that a civilization genuinely committed to the value of the men it employed in its forges would have felt compelled to take. Germany built its industrial dominance on that readiness, on the capacity of its institutions to maintain production tempo across events that should, by any moral accounting that claimed to take human life seriously, have caused a cessation. The rails were laid, the empire was stitched together, the warships were armored. The nation became, for a period, the most formidable industrial power on the European continent. And in the Forge Hall on a Tuesday morning in March, the press was already ready for the next cycle before the man it had just killed had been moved from the floor. The machine flattened rails. It claimed the men who fed it. It built a nation's industrial dominance. These three facts exist together, and they do not cancel each other out, and they do not resolve, and they should not. History that resolves too cleanly is history that has been pressed, shaped under force into a form more convenient than accurate, its internal structure reorganized to eliminate the fractures that the original material contained. The fractures were there. They were documented, they were filed, they were ignored. They are still there, in the archive, correctly referenced, waiting for the next researcher willing to read what the institution did not want read, in the records of a machine that could flatten steel to 1,000th of a millimeter and could not, in 45 years of operation. You find 9 seconds to keep a man alive. The Krupp Company archive in Essen holds 23 kilometers of shelf space. This is a measurement its own documentation provides, offered as evidence of institutional comprehensiveness. The full record of a company whose history spans 2 centuries and whose output shaped the physical infrastructure of a continent. 23 kilometers of document, blueprint, correspondence, ledger, and log. Wilhelm Dressler's 1893 report occupies 6 pages of that archive. It sits in a box with 17 other internal memoranda from the Forge Division's 1891 to 1894 administrative period, behind a cardboard divider labeled with a reference code that a researcher must specifically request to access. It is not cross-referenced in the main finding aid under the heading of industrial accidents. It is not cross-referenced under safety documentation. It is filed under its original administrative category, Internal Technical Correspondence, Forge Division, Unresolved. Unresolved. The archivist who created that categorization in 1952, working through the post-war reconstruction of the Krupp record system, used a word that the Forge Division management of 1893 would have considered merely procedural. From the distance of the present, it reads as something closer to a verdict. The press is gone. The accumulator tower is gone. The Forge Hall has been repurposed 3 times since 1931, and now forms part of a cultural heritage site, the Zollverein Coal Mine Industrial Complex, a UNESCO World Heritage Site, where visitors walk through preserved industrial architecture and read interpretive panels about the history of Ruhr Valley production. The panels do not mention Heinrich Bauer. They do not mention Dressler's report. They describe the scale of production, the engineering achievement, the industrial transformation of a nation. The machine's readiness is not a detail the panels address, but the archive holds it, correctly filed, in 23 kilometers of silence.